Hello and welcome once again for another ES340 video. This is day 7, example problem 2. So air is contained in a closed rigid tank initially at 50 degrees Celsius and 2 bar, and the tank has a volume of 2 cubic meters. The argon is heated to a final pressure of 8 bars. Assuming the ideal gas model with K equal to 1.67 for argon, determine the final temperature in degrees Celsius as well as the heat transfer in kilojoules. So note that because we have this value of K, this means that we're assuming CV and CP are constants. Also that it's ideal gas, right? So the two things together. Generally, for this course, we're going to assume that if it's an ideal gas, that CV and CP are constant, okay? And that's going to help us when we go back to the energy balance equation and start working through things. Okay, so I'm just going to make a note of that just by immediately reading this off. These are things that you should be thinking about when you're working through these problems. Okay, it's an ideal gas. It has the value of K. That means I can figure out what CV and CP are because they're constants. Things like this. Okay, so this is just a way of working through these problems. And it's in a closed rigid tank, so that tells us that the volume is not going to change. Because obviously it can only fill the entire volume of the tank, and it will fill the entire volume, so it's not going to change in volume as it's heated here. So that means that we are going to have changes that are not related to a change in volume. Okay, so let's work out some of the things. The first thing, of course, is that it's an ideal gas, which immediately means you should think something like this at least. PV is equal to MRT. It could have been PV lowercase v is equal to RT, right? If I divide by M to the left side there. But that's it's going to be more useful for us if we put it in this form. So, and we know that V, by the way, since it's a constant, I'm not going to put a V1 and a V2. I'm just going to say capital V is equal to 2 cubic meters. And we also have that P1 is 2 bar and P2 is 8 bar, right? So this means that P1V is equal to RT1 for the initial state, and P2V is equal to MRT2 for the final state, because the mass is also not changing. It's a closed, right? This is a closed system. That's going to be important. So that means there's no change in mass. Okay, closed rigid tank. So what does this mean? Well, we can actually do something with this. I missed the M there, sorry. We can take the ratio of these two things. Usually taking the ratio actually is going to be useful, a useful thing that we can do. So since V is constant, that means that P1 divided by P2, right, because the V's are going to cancel each other, is equal to T1 divided by T2 in this case. Again, this is because it's an ideal gas, because the volume is constant, right? These things, because of that being the case, this is what we get, okay? So that makes it kind of easy to solve for the second temperature, the final temperature, which was one of the things that we wanted to look for. So this means that T2 is equal to T1 times P2 divided by P1, just reorganizing this equation, right? And by the way, the end result would be the same as if you had, figured out, put in the value of R here for argon, figured out the mass. You could have done all of that, but that's a lot more work, I think, than just going this direct route. That's why I did it. So there's other valid ways of solving this problem, but I thought this was the more direct route. So then T2 is equal to, well, 8 bar, I'm doing P2 here, over 2 bar times, well, we have to convert to Kelvin, so this is 323.15 Kelvin. And it's okay if you round this to 323. I'm just going to keep the full 0.15 as well. Oftentimes we'll just round, and that's perfectly valid and fine. Okay, so this is equal to 1292.6 Kelvin. And remember, this is going to be an important thing, is making sure that when we use the ideal gas law, we must use absolute temperatures. That's why I had to do the conversion here to make this Kelvin. But that's going to be, if I want to get the final temperature in Celsius, I'm going to have to backtrack, of course, and that's what I get. Okay, so I can go backwards, and I think that the problem, well, let's go back up and look. It wanted the final temperature in Celsius, which is why I had to do that. Okay, so that's the first part, was finding the temperature. And the second part of this problem is finding the heat transfer. Well, again, we immediately should be thinking we need to go to the energy balance equation. So let's go to the energy balance equation. So we know that delta E is going to be equal to delta KE plus delta PE plus delta U, right? These are going to be 0, as they typically are for gases. There's nothing here that indicates that we have a change in height of the whole mass of the gas or something like that, or a change in velocity of the gas. It doesn't make a lot of sense at this level, at the macroscopic level, to discuss things that way, except in very rare circumstances. We probably will see a problem or two where you do have that, but it's rare. So we're just going to take those to be 0. So that means that delta U is equal to delta E. And also remember that in this case, for this problem, and also that's going to be equal to Q minus W. Okay? And so what that means is then that delta U is equal to Q, because W is 0. Again, the volume of the gas is not changing, right? So we know that if there's no change in volume, there can't be any work done by the gas. So delta U is going to be equal to delta Q. I'm sorry, equal to Q, not delta Q. And so how do we get to delta U? Well, it's an ideal gas. So because it's an ideal gas, we know that delta little u, lowercase u, is equal to m, sorry, not m, CV delta T. Okay, and the reason for that is, of course, it's an ideal gas, and we went over this earlier in the lessons. So you know that this equation holds for an ideal gas, and thus we can actually find delta little u. We're going to have to then multiply it times m. Delta u is equal to m times delta little u, right? We're going to have to find m and delta little u, and CV in this case, because we need to find delta little u, we have to find CV. Well, remember that K was equal to 1.67. That's the ratio of CV and CP, right? And so we know that CV, actually, this came from the video as well, from the lecture as well. CV is equal to R over K minus 1. So that means we need to find R for argon, which is actually 0.2082. Now, how could you find this? Well, we could have said 0.282 kilojoules per kilogram times degree R. This is Kelvin. Sorry, wrong units there. Times Kelvin. How do we know this? Well, this comes from table 3.1 in section, I believe it's 3.11 in your book. Okay, so you can actually get, for some of these, we can actually find the R value right off of that table there. But in general, you can also use table A1 to find capital M, which is the molecular mass. And you can say that R is going to be equal to R bar over M. Okay, so we could have divided by our 8.314 by the molecular mass of argon and gotten a value that's pretty similar to this. And again, everything is kind of rough approximate when we do these things. So if we then take this, we can say that CV is equal to 0.2082 kilojoules per kilogram times degree Kelvin divided by 1.67 minus 1. And that has no units because it's a ratio of those two. Remember, CV and CP, which have the same units. So K has no units to it, and that's going to be roughly equal to 0.3107 kilojoules per kilogram times Kelvin. And now we can find delta U. So delta U must be equal to this 0.3107 kilojoules per kilogram times Kelvin times 1292.6 minus 323.15. So this was T2, remember, and this was T1, and that's going to be Kelvin, of course, and the Kelvins are going to cancel, and we get approximately 301.208 kilojoules per kilogram. And now we need to find the mass because we need to get capital delta U, and the mass is easy enough to find. M is going to be equal to, let's say, P1. It could have been P2 as well, it doesn't matter. P1 V over RT1. And that is the pressure. Well, we have to convert the bars, right? So 1 bar is equal to 10 to the 5th newtons per meter squared, and that means it's also equal to 10 squared kilonewtons per meter squared, which is going to be more convenient for us because we want things in terms of kilojoules. And so we get 2 times 10 to the 2nd kilonewtons per meter squared times 2 meters cubed, 2 cubic meters, because that's our volume of that tank, divided by 0.2082 kilojoules per kilogram times Kelvin. That was our R value for argon, times 323.15 Kelvin. And if we work this all out, it comes out to be about 5.9453 kilograms. So delta U, capital U, is equal to 53 kilograms times 301.208 kilojoules per kilogram, and that was the value that we found up here for delta U, lowercase u, which is equal to 1,790.772 kilojoules, and that is the value that we have for delta U. But remember, up here, delta U was equal to Q. That's what we found from the energy balance equation. And so that means that delta U equal to Q equal to 1,790.772 kilojoules. So that is my Q that I was looking for, the heat transfer. That's all I have for this video. Hope to see you again soon.